Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera. Chapter 1, Reaction Kinetic. The first subtopic 1.1, Reaction Rate. So for this subtopic, we will going to study about rate of chemical reaction, how fast the reaction take place. The first objective, define reaction rate. Reaction rate is defined as change in concentration of reactant or product as a function of time. Consider the following general reaction equation. A produce B. So A is reactant and B is product. So let's say the rectangle below the equation represent the concentration of the reacting species. So let's start the reaction and try to observe what will happen to the concentration of reactant and product. So from here we can see that as a reaction proceeds, the concentration of reactant decrease and the concentration of product increase with time. Second objective, write differential rate equation. Differential rate equation is the equation show the relationship between the rate of disappearance of reactant and rate formation of product. Example 1. Write the differential rate equation for the following reaction. Methane react with oxygen, produce carbon dioxide and water. So how to write differential rate equation for this reaction? First, you need to write rate equal to. Next, look at the first reactant. The first reactant is methane. So for reactant, you need to write negative sign. Stoichiometry is 1. So write 1/1. D concentration CH4 over dt. Next, second reactant is O2 equal to negative sign. For the reactant, stoichiometry for O2 is 2. So you need to write 1/2. D concentration O2 over dt. Next, move to the product. The first product is CO2. For product, you need to write positive sign. Stoichiometry is 1. So 1/1. D concentration CO2 over dt. The second product is H2O. So for product, write positive sign. Stoichiometry is 2, 1/2. D concentration H2O over dt. Look at the methane and CO2. The stoichiometric coefficient is 1. 1/1 equal to 1. So no need to write 1. That is the differential rate equation for the reaction. In writing differential rate equation, the stoichiometric coefficient written in front of differential equation as 1 over stoichiometric coefficient. Negative sign indicates the concentration of reactant decrease with time. Positive sign indicate concentration of product increase with time. D concentration CH4 represent change in concentration of CH4, and dt represent change in time. The next objective define rate law, order of reaction, and half-life. Law or rate equation defined as an equation that relate the rate of reaction to the rate constant and the concentration of the reactant rise to the some power. For example, A react with B produce C and D. The rate law for the given equation is rate equal to K concentration A power M time concentration B power N. So K refer to rate constant. M and N refer to order of reaction, and overall order of reaction equal to M plus N. Order of reaction defined as an exponent in a rate law with respect to the corresponding reaction. For example, A react with B produce C and D. So the rate law for the given reaction is rate equal to K concentration A power X time concentration B power Y. So exponent on the concentration of A and B refer to order of reaction. So order of reaction cannot predicted from the stoichiometry coefficient of the balance equation. It can be determined from experiment. Half-life. The symbol is T half. Is defined as time required for the concentration of a reactant to decrease to half of its initial concentration. Look at the example given. Let's say the concentration is represented by mass. So half-life is the time taken for the mass to become half of its initial mass from 100 kg to 50 kg, and from 50 kg to become 25 kg. The next objective is write rate law with respect to order of reaction. Okay, consider the following general reaction equation. A produce B. So for zero order reaction, the rate law is rate equal to K concentration A power 0. So the reaction given involve one reactant only, and then order for this reaction is zero order. So power on the concentration of A is 0 because 0 order reaction. So we say this reaction is 0 order with respect to A. 0 order reaction means rate does not depends to the concentration of the reactant. If we change the concentration of reactant, rate does not change. For first order reaction, rate law is rate equal to K concentration A power 1. So the power on the concentration of A is 1 because the reaction is first order reaction. So we say the reaction is first order with respect to A. First order reaction means rates depends to the concentration of reactant. If we double the concentration of reactant, the rate will increase by factor of 2 or double. For second order reaction, rate law is rate equal to K concentration A power 2. So the power on the concentration of A is 2 because second order reaction. So we say this reaction is second order with respect to A. Second order reaction means rate is depends on the concentration of reactant. Double the concentration of reactant, the rate will increase by factor of 4. The last objective for this subtopic is write the integrated rate equation for zero, first and second order reaction. Integrated rate law show the relationship between the concentration of the reactant and time. It can be used to determine the rate constant, half-life, and the concentration at particular time. Consider the following general reaction equation A produce B. For zero order reaction, the integrated rate law is concentration A naught minus concentration AT equal to KT, or other form, concentration AT equal to concentration A naught minus KT. So concentration A naught represent the initial concentration before reaction take place. Concentration AT refer to concentration at particular time, T time of reaction, and K is rate constant. For first order reaction, the integrated rate law is ln concentration A naught over concentration AT equal to KT, or ln concentration A naught minus ln concentration AT equal to KT, or ln concentration AT equal to ln concentration A naught minus KT. For second order reaction, the integrated rate law is 1 over concentration AT minus 1 over concentration A naught equal to KT, or 1 over concentration AT equal to KT plus 1 over concentration A naught.